Hello everyone and welcome to today's session on the solid principles. Do you know friends that Robert C. Martin introduced the solid principles in his work Design Principles and Design Patterns in 2000. Michael Feathers, who introduced us to the term solid, expanded on these ideas. These 5 ideas have changed the field of object-oriented programming over the last 20 years, transforming the way we write software. Now before we discuss today's agenda, do not forget to hit the subscribe button and click the bell icon. So let's discuss today's agenda. First, we are going to start with single responsibility principle. Then we will discuss about open-close principle. Moving ahead, then we are going to discuss about Liskov's substitution principle. Then we will learn about interface segregation principle. And at the end, we are going to discuss about dependency injection principle.
So let us start with single responsibility principle. This concept states, as one might imagine, that a class should only have one and one responsibility. Furthermore, it should only alter for one reason. But how does this principle assist us in developing better software? Let us look at some of its advantages. The first one is testing. A single responsibility class will have considerably fewer test cases. Second, it would have lower coupling. When there is less functionality in a single class, there are fewer dependencies. The third is organization. Smaller, well-organized classrooms are simple to find than a large and disorganized one. Let us look at an example to further comprehend this notion. Now, we will look at a meal delivery app that accepts order and calculates the bill and delivers the food to the customers. We can create the distinct class for each of the jobs to be completed. And then the main class can simply invoke those classes to complete the task one by one. Let's look into the code and see how SRP or single responsibility principle applies to the following. So now we have a customer class with customer properties. So let's look at what this class contains. So I have initialized the string name, which is private, and then I have address, which is of type string, and it is also private. Then we are storing the name with a function called getName, which returns basically the name, and its access modifier is public. Then I'm setting the name with the property as string and adding the name as a constructor here, basically where this dot name equals to name. So this holds the property for the name. Similarly, I have another property or attribute as address, so which I have declared as public string get address, which is returning basically the address. Then in order to set the address, I have used the set method where I have added the string address, and I have also used in the constructor format this dot address equals to address. So this all the attributes contains in a customer class. Similarly, I have created a class order in which the following attributes are present. The first is customer, which is private. Then I have an order ID, which is also private. Then I have a string item name and quantity and total bill amount. So this all attribute contains in the class order. There are certain methods also introduced in this. Suppose public customer, where I am usually getting the get customer method, which actually returns the customer. Then I have declared the set customer, okay, where it is taking customer as one attribute, and I have set this using this customer equals to customer, as we do in Java, which I have set using this customer equals to customer. Next, where I have set this using this dot customer equals to customer. Next, I have an order ID, which is of type string, and this method returns the order ID. Next, we are setting the order ID, and order ID is randomly generated. That's why we have used random, and it adds up to any next integer, still 500. Now we have a string get item name, which returns the item name, and there is a set item name, which takes string item name as its property. So I have set this using this dot item name equals to item name. So any item name can take this attribute here in this method as set item name. Then I have set the order ID with the attribute set item name. Similarly, I have added public and get quantity, which returns the quantity. Then we have set quantity which takes up the integer quantity, and I have make this as this dot quantity equals to quantity. Similarly, we have get bill amount method and set bill total amount method. Now next in the order chart, we have prepare order, where we are printing out basically this customer name and who has ordered basically, and this dot get item name. So we have declared this earlier. So this was our class order, which contains the following thing. Now similarly, the bill calculation class computes the total bill and stores it in the order object. The delivery app has only one task: deliver the order to the consumer. In the actual world, these classes would be much more complex, requiring their functionality to be subdivided into numerous classes. For example, the bill calculation logic may necessitate the implementation of some sort of lookup feature in which we check up the price of each item in the order against some kind of database and add them up, add the taxes, delivery charges, and so on to arrive the overall price. Depending on how the complex code becomes, using SRP's principle, we can avoid the cohesion and our modification of anything which we want to add becomes pretty easier. If we talk about the void calculate bill function, or particularly about this bill calculation class, if we talk about the functionality of it as well as the order delivery, if it was added in the same class, then that class get modified whenever the bill calculation logic or the delivery agent logic needs to change. And this is what somewhat goes against the single responsibility principle. So I want to repeat again. So for each of the classes, suppose we had these classes as customer, which had its own responsibility, and it took the attributes as name, address, and used the methods called getName, get address, and set address. Similarly, there was a class called order, where we had the following attributes and used certain methods to return some of it, such as customer is first thing it's returning, then it is setting the customer, then order ID was there, then item name, then quantity, then total amount bill, and then what to prepare. So this was a responsibility of this class called order. Similarly, then there was another class with the functionality called bill calculation, and this has the responsibility of calculating the overall bill. Then finally, we had our delivery app. Okay, so in this, what we are doing basically, what was the order was there, it should be ordered. So we had that functionality all over here, or basically the void delivery function takes the responsibility of delivering it. So each classes had their own responsibility, which was basically getting you an idea about single responsibility principle. Now let's check on to the next one. The next principle we are going to discuss here is open close principle. Now, if you were to ask me what is the most important feature of any software is, I would say that it is the mutability of any project over the time. Software is created to solve a specific problem or meet certain need in the actual world, and the requirements are always subjected to change. Software is both abstract and malleable. Given the importance of this component, we developers must take it seriously every time when we build a project, including the use of approaches that allows us to have a code structure that minimizes the likelihood of introducing new issues when the business requirement change. That principle, if we are talking about, you are right, is open close principle, which asserts that a class or an object should be open to extension but closed to alteration, is one of these alternative strategies. But what does this mean in practice? It means that if a certain class must be changed due to a new business requirement, it is preferable to build new code for these changes or a new functionality rather than impacting the existing one where it is possible. But now it's time to put the theory into the practice. Let's see a code what I have created for you. So we have a basic calculation app in Java where I have our first class as addition.java, where I have used the first operand, the second operand, and the result as a third operand. Basically, these are our variables here. So I'm basically doing the addition in this class. Okay. Next class we have subtraction.java, where we are declaring our first operand, second operand, and result as 0. Then in this method, what we are doing basically, here we are calculating our subtraction. Then we have interface called calculator. Then, then in this class called simple calculator.java, what I'm doing basically, I'm implementing the interface of iCalculator and basically calculating the addition and subtraction. Now, if I talk about this following code, this module looks excellent and serves its function of addition and subtraction. However, if a developer wants to add multiplication capability into the client application, he has no choice but to change this simple calculator class, a code inside the method calculate. And this is basically not compliant to the open-closed principle. Now let's see a code that is open-closed compliant. Now let's see a code that follows open-closed principle. Now in this example, what we have in the addition class, what change we have done is I have declared a new function which performs operation. Then the same thing I have done in subtraction, where I have declared void perform operation function, which is actually doing the subtraction in this case and addition in this case. Now when we are creating an interface of calculator all over here, same thing as we have done earlier, but in the simple calculator.java app, I'm basically calling this perform operation. So suppose if you are going for addition or going for subtraction or even going for multiplication, which I have declared this class all over here, it's going to perform that particular operation. So you can modify n number of times without doing changes in this particular class. So this particularly states open-closed principle. Now let's discuss about Liskov substitution principle. Do you know, friends, that the object of a superclass must be replaceable with object of its subclass without interrupting the application? According to this principle, it necessitates that the object of your subclasses behaves similarly to the object of your superclass. You can follow this by few guidelines set by Burton Mears and designed by Contract Notion. The functions that use base class references must be able to use derived class object without actually knowing it. In other words, derived classes must be interchangeable with the base class. A subclass overridden method must accept the same input parameter values as a superclass method. That's it. You can create a less stringent validation criteria, but you cannot enforce tougher ones in your subclass. Otherwise, any code that uses this method on a superclass object may throw an exception if it is called on a subclass object. The method returns value is subject to the same rules. The return value of a subclass method must follow the same constant as the result value of a superclass method. Now let's look at an example to understand this principle better. To ensure this, it follows the Liskov substitution principle. We must implement some of our own checks. In the best scenario, we can do certain code reviews and test cases to test this. Let's look at the classic example of rectangle and a square. Here a square class inherits from the rectangle, and this represents kind of a is a relationship which states that square is a rectangle. The rectangle class in this case is represented all over here, where we have length, we have breadth, which takes getLength and returns length. Then we have setLength method, which takes length as a parameter. Then similarly we have getBreadth, and for the setBreadth, same thing applies all over here. Then we have a function called area, which returns length into breadth. Okay, so this is basically a rectangle class. Similarly, a class called square, which inherits from rectangle class all over here, so which extends rectangle. And similarly, we have setBreadth method, which is used earlier, overriding basically, and setLength method all over here. So what basically I'm trying to say, according to this principle, the function that uses base class references must be able to use the derived class, the objects of it, without actually knowing it. Thus, in the following example, the method calculate area, which utilizes the reference rectangle, should also be able to use the object of the derived classes such as square and meet the conditions set by rectangle specification. Let's examine the calculate area method in the following code. Okay, so if we examine the calculate area method in the following code, it is worth noting that according to the definition of rectangle, the following must always be true for a given data. Length must always be equal to the length supplied as the method's input. Length and breadth must always be the same as the breadth supplied to the method as an input set. The product of length and breadth must always match the breadth area. If we try to construct there is a relationship between square and a rectangle so that we can say square is a rectangle, the code below will behave strangely if an instance of a square is provided. Although the program will stop if the check for an area or check of a breadth will fail. An assertion error will be thrown if the check for area and check of breadth will fail. So in this case, you can understand what the problem we have for rectangle class and the square class. Now let's look at the another code which I have declared all over here, basically, which is kind of an updated code and which follows the LSP's principle. So it is worth noting that according to the definition of rectangle, the following things which I have said earlier will be true. For example, length must always be equal to length supplied by the method. Similarly goes for breadth, So I have set breadth as 2, set length at 3, and I am using the assert method all over here to get area and print error area equals to R. So from this code, the expected behavior what we are seeing that the area of rectangle is equals to 6. If it is not, then it's going to print an error. Similarly, I have used the assertion for the same thing, you know. So if we try to construct a is a relationship between square and rectangle so that we can say square is rectangle. So after telling the definition about length and breadth, can you see what is the issue with the square rectangle is a relationship in the given code? You can see because sides of a square are equal. The square class does not require the methods like set breadth or set length, and this is inefficient. Consider the possibility of hundreds of thousands of square objects. To prevent throwing errors, the LSP demo class would need to know the specifics of the derived class of rectangle, such as square. The modification to the existing code to handle the derived class violates the open-close concept in the first place. So as you can see, the problem all over here in the square because it doesn't need the integer breadth and length, set methods or get methods. Similarly, for the same purpose we have used in the demo class, the assertion to see that it does not violate the open-close principle. Now let's discuss about interface segregation principle. Declaring methods in an interface that the client does not require pollutes the interface and causes it to become bulky or fat. Interface segregation, which basically indicates that the bigger interfaces should be divided into smaller ones. By doing so, we can ensure that implementing classes are only concerned with the methods that are relevant to them. Now we are going to write some code all over here to demonstrate the interface segregation principle. So here we are going to write some code for our burger shop where customers can purchase a burger, fries or both. We have opted to include all the methods in a single interface because a customer can order fries, burgers or both. Now in order to construct a burger only order, we must throw an exception in the order fries method. Similarly, we need to throw an exception in the order burger method for a fries only order. This is not the only disadvantage of this design. When we update to our abstraction, the burger order service, fries order service classes will also have an unintended consequences. Assume that we have decided to accept order of fries in pounds or grams. In that situation, we almost certainly need to add a unit parameter to the order fries. Even though burger order service does not use this method, this change will have an impact on it. So we confront the following issues in our code as a result of violating the ISP principle. Client developers will be perplexed by the ways they don't require. Side effects make maintenance more difficult. A change in an interface causes us to change the classes that do not implement the interface. For example, we can refactor our code for a burger place code to have separate interfaces for burger order service and fries order service. So you can see the refactored code all over here where we have the interface for burger order service and fries order service. When we have an external dependency, we can use the adapter pattern to abstract away the undesired methods, which allows us to utilize an adapter class to make two incompatible interfaces compatible. Let's say order service is an external dependency and we can change but we must use to place an order. To adapt order service to our target interface, burger order service will use the object adapter pattern. We will do this by creating the order service object adapter class, which will contain the reference to the external order service. So, when a client wants to use burger order service, we may wrap the external dependency with the order service object adapter class. So you can see all over here. So you can see how the way we have refactored our interface segregation principle. I hope so you have got some idea regarding this. Now let's move to our last one, that is dependency. Dependency injection is a design technique that removes the dependencies from programming code to make the application easier to manage and test. Because of dependency injection, our computer code is loosely connected. There are basically three types of dependency injection: constructor injection, scatter injection, and interface injection. And today we are going to see one type of injection that is called as constructor injection. While the constructor injection uses a constructor to inject the dependencies, scatter injection will take an advantage of the setup properties to inject the object dependencies. Now let's see the code and understand how we can implement dependency injection principle. As you can note how the dependence is given through the business logic class constructor. Interface injection injects the dependencies via interfaces, putting interface injection into this action. So when we start and look at this code, the code below demonstrates three classes: entity base, employee, and customer. Entity base is a parent class of both employee and customer entity classes. So we have the public class business logic, which states inside this we have business logic, which take business as entity. Okay, we have created our constructor all over here. Now consider the following interfaces: the iCustomer repository and iEmployee repository interfaces. The iEmployee repository interfaces will inherit the iRepository interface. The base interface here is IR repository, which declares a few repository methods. Okay, so you can see all over here that we have declared few methods with iRepository. So you can see we have iCustomer repository, which takes and get single int customer ID. Similarly, I have declared another interface which also uses the get single method all over here. Okay, so basically these are taking the customer ID and it's taking the employee ID. Now it should be noted that the get single method is only available in the iCustomer repository, iEmployee repository interfaces. Now that the interfaces are in place, let us design the actual class that will conduct the CRUD operation on the customer and the employee instances. The employee repository and the customer repository classes are depicted in the following code. Okay, so this is your following code all over here. It should be noted that both of these classes implement iEmployee repository and iCustomer repository interfaces. Now, as you can see, the business logic class is represented by the following. And please keep in mind that this is a general class. You will need to extend it if you wish to offer a specific implementation. For the purposes of this example, this class has only one attribute of type IR repository named repository. If you take note of these repository instant, which is inserted via interface injection. In the following code, we have seen that we have injected our repository instance all over here through the interface injection. So this was basically an example of dependency injection, what we have seen right down here. Hope you would have got some idea how we can inject the dependencies, So this was an interface dependency injection. So that was all for today's session. Hope you would have got some idea regarding the solid principle that we have discussed today.
Just a quick info, guys. Intellipaat provides Java certification online training, mentored by industry experts, the course link of which is given in the description below.